Okay, we are talking about slightly soluble salts today. So I'm going to kind of define this for you because slightly soluble salts might be a little confusing considering the fact that we usually classify salts as either completely soluble or insoluble, and there's actually some in between there. So in Chem 161, we said we have the set of solubility rules, and if you go by the rules, you can be like, okay, well, this thing dissolves and this thing doesn't. Well, of course we lied. It's not black and white like that. Because 162 delves into the equilibria of everything, there's always going to be a teeny tiny bit that dissolves of something that's, quote, insoluble. And there's always going to be a limit to what can dissolve of things that are soluble. So that's where we're going to go in. So the solubility rules in Chem 161 were really, those were black and white, but they're really not black and white like this. It's not black and white. Essentially, everything can dissolve at least a little bit. Everything will dissolve. I'm going to put slightly. Okay, it's just what scale. Does it dissolve really, really well? Or does only a very, very small amount dissolve into the solution? So we're going to look at these slightly soluble salts, and they're governed by equilibrium. So we're going to have K values, just like we have with all of our other equilibria. So when we are looking at salts, okay, salts being ionic compounds, okay, so salts being ionic compounds, okay, when they dissolve, they dissociate, right? So these are all going to be based on dissociation equations. Okay, so if you look at the solubility rules and you see check for PbCl2, so one of the rules is chloride ions, so things with chloride in them, are always soluble unless they are with, and then there's three exceptions, one of those being lead. So per the rules, lead 2 chloride is insoluble, okay, meaning it won't dissolve. Now, in reality, it's just not very soluble. Okay, so if I write out, this is the dissociation equation, okay, which just shows what happens when it goes into water, it splits into its ions. It's essentially just a very small value. Okay, so a small K value means not very soluble, right? Because a small K value means there's not very many products because it's products over reactants. So that means it hasn't shifted to the right very much. Okay, so small K means it's not very soluble. All right. Again, so if you're trying to be like, put those numbers together, if I write a K equation for this equation here, it would look like this, right? Pb2 plus times Cl minus squared. Okay, and there's nothing on the bottom because this is a solid. So it's just the multiplying the concentrations of the ions, essentially. And so if this is really small, that means there aren't very many ions that actually went into solution. Most of it stayed as a solid. Okay, so this K value is called KSP. So you'll notice the little SP down here. We've had KA, we've had KB, KC, KP. The little letters at the bottom just denote what kind of equilibrium we're talking about. All right, so KSP is called molar solubility, okay? And this is the solubility product constant. That's what the S and the P stand for. So just still constant, K is a constant for specific temperatures, okay? And we calculate it with, the dissociation equation. Okay, that I just wrote above as an example. Okay, so it is the product, meaning multiplied, right, of the ion. So let's put of the ion concentrations, right? So like I said above, if I were to calculate KSP of lead chloride, it is essentially just the lead ion multiplied by the chloride ion concentration squared. Okay, so it is the product of those two, and it's always only going to be two ions that are part of that actual compound. Okay, so this term molar solubility, molar meaning molarity, right? This is a term we use to describe how soluble something is. Molar solubility is the moles per liter, so molarity, right? This means molarity. And when we're describing molarity, we use the term molar. It's the moles per liter present at equilibrium. Okay, so this is where this whole equilibrium thing comes in. We are, of course, then going to be using ice tables to determine how much there is at equilibrium. Okay, so molar solubility in regards to our ice table is X. So if I'm asking for molar solubility, I want that X value. That's how soluble those ions are. Okay, so it is important, and I kind of starred this because if you don't write your dissociation equation correctly, you are not going to get the correct value. For example, this one, chloride is squared, so you can't forget those coefficients in there. These ones are not going to be all 1-to-1 ratios like they were for acids and bases because we can have all different numbers of ions depending on what the charges are. Okay, so we're going to do example number 1 here. It says the KSP for calcium fluoride is 3.4 times 10 to the negative 11. So really not very soluble. What is the molar solubility? That means I want to find X of CaF2 in moles per liter, right? That's just molarity, capital M. Okay, so I'm going to write my dissociation equation and set up an ice table, right? Because this is all about equilibrium. So CaF2, when it dissolves, would break into a calcium ion, which is 2+, and 2 fluoride ions. You're always only going to have 2 things. Okay, there's a calcium and a fluoride. In this case, there's always a positive thing and a negative thing. Okay, so I'm going to go with an ICE. This is solid, so that part actually doesn't matter. So you're always going to be able to get rid of that. I don't start with any ions, but when it dissolves, then I'm going to be plus X and plus 2X. Okay, so this one is going to be X and this is going to be 2X. Okay, so if I were to write the KSP, I'm actually going to write this out first. According to my equation, it should be calcium times fluoride squared, right? So then I'm going to put my equilibriums into my KSP. So KSP is going to be X times 2X squared. Okay, now algebraically, don't forget that this 2 goes to both of these things. So if I multiply this out, it's actually 4X cubed. Okay, so KSP equals 4X cubed. Well, I have the KSP, so it's really 3.4 times 10 to the negative 11th equals 4X cubed. And this is pretty easy to solve for X, right? Just divide by 4 and then take it to the 1/3 power. And you would get, in this case, that X is 2.0 times 10 to the negative 4th. And that is a molarity. These are ice tables. Okay? So this is what I was asking for. I wanted the molar solubility. And this is like the solubility of the ion. So it's 2 times 10 to the negative 4th molarity. That is the answer. That's it. Okay, so we're going to look at a couple of other things that are slightly soluble and how the equilibrium is affected. Hydroxides are some of these. Now, strong bases like sodium hydroxide, calcium hydroxide, those do completely dissolve. So they would completely go to the right in the forward direction. They have a huge KSP, but we can have hydroxides of other things that are not strong bases. This would be considered a base because it has hydroxide, but it is not one of the strong bases because it's with iron, not a group 1 or a group 2 metal. So FeOH2 would be basic, but it's really not very soluble. And if you check your solubility rules, we would say it is, quote, insoluble, which means a little bit of it will dissolve. Okay, so we're going to talk about this compound, and it all works exactly the same. I am first going to write my dissociation equation for iron 2 hydroxide. So iron, OH2, right, that would be my solid, breaks into iron 2+ in this case, and 2 hydroxides. These are both aqueous. Okay. Now, since I have these hydroxides here, that is going to affect the pH. So we are also going to be looking at pHs if these things can cause acidic or basic solution. So if it's got an OH- in it, of course, it could cause it to be basic. Okay, so example number 2 says the pH of a saturated solution. Saturated solution means it's at equilibrium. It means it's dissolved as much as it can. So I'm going to put that dissolved as much as possible. Okay, but saturated you can equate with at equilibrium. Okay. I said the pH is 9.07. What is the KSP for FeOH2? So if I'm looking at this problem, I'm like, okay, I have a pH. So I'm going to write that over here. I've got pH is 9.07. Okay, and what can I find from pH? Well, I can find H plus and I can find OH minus, which in this case, I'm going to want to find OH minus because I've got OH minuses in here. And I also have KSP, which means I'm going to have to write my dissociation equation and do an ice table for this problem. Okay, so I'm going to go ahead and do that. Got FeOH2. I wrote this above, right? Breaks into Fe2 plus 2OH minus. I got a C, E. Now, I don't have a starting concentration that I gave you. Okay, so I do have a pH. So we're going to do this just like we did before. When it dissolved, I had none of those things. Okay, plus X plus 2X, X and 2X. So this means, and you're going to probably be able to start skipping writing the whole ice table. It's going to be the same as it was for the calcium fluoride that we did above. It's X times 2X squared, which is going to be 4X cubed. Okay, so anytime you have something that breaks into essentially a positive ion and 2 negative ions, or 1 and 2 of the other, it's going to be 4X cubed. Okay, so you can probably start dropping the ice table, and that's okay. All right, so can I solve for X? What can I solve for? The only other piece of information I have is that pH, right? So at equilibrium, the pH is this. Now that also means that the pOH is 14 minus that, which is 4.93. And from pOH, I can find OH minus concentration, right? 10 to the negative 4.93 is 1.175 times 10 to the negative 5th. Well, this is OH minus, remember, when it's saturated at equilibrium. So that means that is this value. Okay, so that is from the pH. Okay, so I'm going to take this, and it is this guy. So 2X equals 1.175 times 10 to the negative 5th. And that's how I'm going to solve for X. So I'm just going to divide by 2. My X value is 5.87 times 10 to the negative 6th. Now I can plug my X value into my KSP. So cube it and times 4, and your answer is going to be 8.1 times 10 to the negative 16th. So this is a very small value. It is not very soluble. Okay, but that pH actually got us to the KSP. So since this was a pH one, I used the pH to find hydroxide. This is also a KSP problem, so I set up my ice table in order to do the KSP part, and that is how I solved for X and then plugged back into KSP, right? We are going to do one more. I want you guys to try example number 3 and then check back, all right? So go ahead and pause it. Okay, so if you got 7.8 times 10 to the negative 12, you did this right. I wrote out my KSP equation. I kind of dropped the ice table. I know this is going to be 2X and this is going to be X, and KSP is going to be 4X cubed. The other piece of information I gave you in the problem is that the concentration of the Ag plus ion in a saturated solution, remember saturated solution means at equilibrium, is 2.5 times 10 to the negative 4th molar. So that meant this 2X value, which is silver, is 2.5 times 10 to the negative 4th. So I set those equal to each other, solved for X, then plugged it in and got my KSP as 7.8 times 10 to the negative 12.